easier, I will make recordings. This will help. And I'll put them on YouTube channel. You can find them under my name. I will publish links in this study system. Okay, here I am. Recording start. So, what about this course and what we are doing here? What do you know about electrotechnics? It's a basics of electrotechnic theory, yes? First part. The second, circuits theory. Theory of signal, it's what goes beyond circuits theory. It's actually it's forks. Third part is theory of electromagnetic fields, and in parallel goes theory of signals. It's, let's say, super advanced circuits theory. We don't need complete course. It's very complicated. Complete course of signal theory, signals and systems, is so complicated as quantum mechanics. They share the same mass. It's really quantum mechanics of electrons. We don't need such high. We need, let's say, applied for power system, for electrical systems. So, what is signal? At this level, it is not important. Voltage, current, power, pressure, anything. Under signal, I will multiple times write this. We will consider any physical matter what can be observed in time. It is not important. I can, students count at a lecture. It's a signal. Anything, voltage, current, pressure, or I don't know, engine crankshaft position. Everything is a signal. Any matter, physical matter we can observe in time is a signal. What kind of signals we can expect? See, for human being, for Homo sapiens, it's easier to deal with some matter when it can be, let's say, accounted, put a tag on it. This one is red, this one is yellow, this one is discounted. It's easy. For signal, first we have two large group of signal. One is determined signal, and a second group is so-called stochastic or probabilistic signal. If we have mass description for signal, it may be complicated, but if we have mass description, allowing us to exactly name signal value state for any time moment starting from the minus infinity and ending at infinity, its signal is determined. For stochastic signal, picture is a bit different. Let's say now recording is on the way. Can we predict recorded level next minute? Complicated question. To predict recording, we should know what I'm trying to tell. If I don't know it. But let's say we can bit analyze limits. Possibility number one, opens this door and our rector stands here. Silence, only clock ticking. It should be a lower level. Yeah? It's a baseline. Another version, opens doors and bunch of clowns. It will be higher level. So, recording will be somewhere between lowest and high. We can draw a probabilistic curve. We can say it's a probability signal amplitude, something like this, maybe normal, maybe some other distribution. Okay, it's a Gaussian curve. So it's a probabilistic characteristic of the signal. Signal is probable from something. It is not easy to operate with stochastic or probabilistic characteristic. So when possible, we try to replace real probabilistic signal. Reality is stochastic. Reality is, in our work we speak about possibilities. But to make our life easier, we often replace real probabilistic signal with ideal deterministic test signal. Or, there are two ways. Or use most probable, or in power engineering, often we use ideal, let's say, echelon signal, ensuring system operatable in any possible condition. One of the very popular things, any protective equipment should survive short current, meaning it should be capable to operate 5 seconds, no longer, when current reaches 40 times from the normal. So if we have equipment, is called protective relay. And I'll show it to the camera. It's a cassette of input signal. Input rec. You can see this nice current transformers. Rated current for this transformer is 5 amps. So they are for nominal regime up to 5 amperes. But they are tested, and all this is tested, designed, tested and approved to withstand 200 amps within 5 seconds. It's a short regime. So, when we test this equipment, we should include this test signal and corresponding to the short circuit. It should withstand failed regime. Takes for meters. Demo relays. What's easier to disassemble? This analog power meter. With analog. For power meters, usually standard requires only 20% overload capacity, only 20%. So the signal will be 1.2 of the nominal. This one, you see, didn't hold. So we often replace real probabilistic signal with test signal, ensuring system will operate. So any real signal, any real regime, any real mode will work if we tested system on the maximum possible. Okay, next idea. Next idea is continuing. Let's say signal representing minute. We can split it in minutes. Yeah, and if every minute can be split in seconds, and every second can be split in nanosecond, so I'm continuous. Our reality, our world is continuous. We will not operate at so micro levels when time can be discrete. No, our time is continuous. Our signals, real signals, are continuous. But let's think. I have an experiment. Can I have an experiment? Why not? I take one student, one luck student, here. Take a voltmeter and make me recordings of my experiment. What student will bring me? Nice table. Time, voltage, 1 minute, 2 minutes, 3 minutes, 4 minutes. I'm going to cafe. Oh, let's say 5 volts, 7 volts, 3 volts, 5 volts. Measurement table. Something familiar, isn't it? Time, voltage. I don't know, maybe something like this. Y is a voltage as a function of time. But what did I get? Number 1, number 2, number 3, number 4. I got 3, 4, 5. I've got measurement table. Yeah? Can I determine what is the element of this table? Take a look. Timing interval between measurements. This one is 1 tau, 2 tau, 3 tau, and so on. The red lines represent to me a signal, voltage. Voltage was continuous. These guys represent my voltage, but as a function of step time or discrete time. Can I tell voltage magnitude at this point? It may be this, or maybe something like this. Do I know it? No, not measured. What's the value of signal between measurement points? Unknown, undefined, unmeasured, unknown. White line represents continuous signal. Orange start points represents signal as a function of discrete time, interrupted time. Let's say in a simple, when discrete time is taken on the even with constant time step, it will be signal of discrete time. Why we are talking about this? Student experiment measurements. It's all blah blah. But any digital system Analog system worked in continuous time. Any real digital system, any microprocessor, computer, any digital system operates in discrete time. Digital time is discrete. Our time continuous, digital time discrete. It's always a time on, let's say, one click of processor clock. Digital time is discrete. And when we try to perform some digital signal processing, or we would like to make some function, some algorithm, something, it all happens in reality in discrete time. Okay, continuous and discrete time. For us, discrete time signals are representations of continuous signal in the, let's say, some digital device memory, computer memory. Not when someone plays guitar, sound is continuous. Recorded on a compact disc. Who records compact disc today? It's become discrete. Digitalized as MPEG stream, it is discrete and compressed. Okay, let's go forward. We deal with power systems, with electricity systems. For us, first important. Let's have a dichotomy. What's dichotomy? There are periodic and non-periodic or aperiodic signals. Mathematics strict, the idea of periodic signal should be related to continuous signal. But, okay, with the Knoll conclusion, we can operate in discrete time with the idea of periodic. What's the idea? Periodic, aperiodic. If we have signal such what it repeats itself, okay, not an ideal, something like this. So any point of original signal is repeated of period. Capital, it's a repetition time. Here, m is an integer. Okay, minus infinity m equals 1, 0, 1, infinity. Here m is infinity and E capital is a repetition period. So if signal repeats, we will call it periodic. Ideal voltage, periodic. Ideal current, periodic. Sometimes students are periodic. Sorry. If signal repeats, it's periodic. Non-periodic, I often will use aperiodic. Never repeats. It's continuous, it's determined, but never repeats. Classics. Classics of non-periodic signals from the circuit theory. Are you familiar with circuit theory? Something familiar? Here, let's say voltage is coming down. What will be voltage if you are familiar? What a silence. Time, voltage, okay, green. It will be 0 before 0, and when switched at the computation moment, this will be E power of, here, alpha is a time constant, 1. Classics of non-periodic or periodic signal. Capacitor discharge. Seen in circuits theory, or I should call VTOLs. Who's reading circuits theory? Or you don't have it first? We'll start. So, I'm in forward. Okay. It is classics, capacitor discharge. Wait, I will show it. Why? Is it continuous? Yeah. Is it determined? Yeah, I can calculate exactly value of signal at any time. Repeats? No. We have pulse. In technical, it's such impulse or pulse. Pulse type of signal. What can I do? What can I do? I can take a generator producing sequence 1, 0, 1, 0 with a period T capital and control the switch what will I get? Original one. Next computation, next. It's a pulse sequence. Time. Signal being a sum of pulses. It's a sum of pulse sequence looks like periodic signal. If you take, for example, control signal from engine drive shaft, you will get pulse on every revolution. When the first cylinder is a high cylinder, first piston on the high point. It's periodic. Yes, in fact, it's periodic, but it's made artificial as a sequence of aperiodic signals. So we can operate as it would be periodic, but with caution. In strong definition, sequence is not an exactly periodic signal. It's a combination. It's a superposition of multiple signals. You already late. It is not my problem. Yeah. So, sequences. Well, sequences. We can work with them as a periodic signal, but with caution. What good about periodic signal? Often it's enough, it's sufficient to calculate. We are interested in some regimes. Okay, we have some questions. How will operate network? Will it operate at all? With periodic signal, often it's enough to calculate one period because it's repeated. We know what all other periods are the same. So, let's say we need rated power. It's enough to calculate one period, and we will get it. With sequence, often, or if our mass, we have developed some mass idea, if our idea work for one period, they will work for all. But, I should show one thing. It's okay for stable regimes, not for transients. Often, experienced people confuse stable regime and transient. Transients, you need to be much more accurate when you consider transient regime. Tree just fallen on the line, everything in progress. The fault is in progress, it's not stable. There. Moments of fault. Real, it's 300 kilowatts line. It's artificial made, but it's a real shot. Okay, at this moment it's a philosophy. This philosophy will become a mass. First it should be in circuit theory. Okay, I understood what I'm going parallel. One special group of signals like cosine or sine. Something familiar? What I should have? 2 square roots from 2. And what's the period? If I put my finger here, what will be period? I will not put my finger. I don't have spare fingers. If we have 50 hertz, what will be period? Yeah? Timing is 20 milliseconds. 50 hertz means 50 revolution per second. Angular frequency, and period is 1 against frequency. Angular frequency will be 100p radians. I can write, say, 230 volts, square root from 2 is sine 100p such type of signal, pure sine, pure cosine, are solutions of the oscillation equation, or another pure sine sound. Ideal pure sound of tuning fork corresponds to this mass. So, Such signal earned name harmonic. Harmonic signal, pure cosine or pure sine, pure sound. Harmonic signal are determined, are periodic, are continuous. Ideal voltage, ideal current will be harmonic. Ideal, not existing in reality. Okay. Let's go forward. Let's go forward. What I have here, it's a source of test signals. Produces harmonic signals. I can change frequency. I can change magnitude. What I'm changing now? I have string cosine. What I'm changing? What's tone increases, that's mean what? What changes in this equation? T, and frequency increases, T decreases. And now amplitude. It's called amplitude. Nice to hear, but maybe better to see. How can we visualize signal? I would like to show one beam. Not of the only power supply. Making happen safety. Case one of the Crookes experiments. Professor Crookes developed a set of demonstrations, and I'll use one of them. What some wrong. experiments. Nice green line. You see a green line. Cook's idea, vessel with high voltage source, diaphragm. Voltage is so high that electron can leave the cathode and fly free. But on the way of the electron, screen is located. Covered with zinc sulfide based coating called luminophores. When it's being subject of bombardment by electrons, it emits visible green light. So we see an electron beam here. We see I can take magnet. Can you see? Electron beam is a current by its nature. And Ampere teaches us see? It's a not Ampere but Lorentz. It's a Lorentz force. Magnetic field deflects electron beam. I'll take short screen. Crookes schematics also incorporates two electrodes, like this. Deflection plates. Let's say this plate received a positive charge and this one, oh sorry, it's negative. What will happen? The electron beam will go up. And in opposite, if I charge this negative and this one positive, it will go down. So beam will follow voltage between these plates. We can try it. I just need a voltage source. Voltage source. Hand current generator. Why not? I have that voltage source. Can you see? I'll try slow. My electron beam follows the voltage of generator. I have a very low inertia system with, and you see beam follows. Oh, it's interesting. If magnetic deflection is relatively slow, it was used in all TVs. Electrostatic deflection is quite fast. What I'll need here. Idea of cathode ray tube. Cathode ray tube. You can see here one set of the deflection plate and another one here tip. Think I can evacuate it. Hot cathode. Let's say 1000 volts. This is E. This is eager deflection plate and last fuel. Here we will need luminophores coating of zinc sulfide, let's say. Trail of electron. If I have deflection system like this, 1x, 1x, I can draw my electron beam in any direction. I have two coordinate system. Let's this one is no longer needed, but I will need a scope. Better do it with the old model. This one will work for us. A long while. this one, this. Okay. What do we see? I took voltage from my test signal generator and use it for horizontal channel. I have how many channels? Two. Horizontal movement and vertical. Why I'm using only one? Time to bring second generator. It's 20 hertz. A signal from second generator. And now let's say 400 hertz here. And I got something. What's the name of it? The Now we have two sine type signals. One from the larger generator moving on a horizontal direction, and another one also sine, very pure, less than 1000% in purity. Used as a vertical movement. What's the name of it? Have you heard? Lissajous figure. It's a figure of Lissajous. Equal frequency. I can take this one. I need 8. 2 against 1. Vertical 800 Hz, horizontal 400. Research figure. When figure is stable, frequency ratio we can draw a line and common number of common points gives us a frequency radius. Now I have 900 hertz something. Another nice whistle figure. 1000. It's 160. One more research figure. Earlier physics teacher loved research figures. What about now? Have you seen this before? No. But it exists. They are better on analog scope. I can go. "200 Hz on a vertical channel and 400 on horizontal. And now moment physics teachers do not speak about. It's a chart. Yeah? It's a two-dimensional chart. What we have on a horizontal? Wait one moment. Usually charts are something, let's say x, y being a function of x. It's usual chart, yeah? What do we have here? Of signal from the first generator, yeah? So here x is actual a first signal as a function of time. And what we got here? Also signal. So here, and this line, I don't know, is a second signal displayed as a function of the first signal. Actually, we see a representation of this signal as a function of the first signal. We see nothing else but functional representation. The form of chart we will see depends not only on Y channel signal, but also from the space where we, let's say, visualizing or representing. We see now second generator signal imaged in a space of the first generator signal. If we would like to see it as a time function, we need to use, it's called sawtooth, where this part is cut. If we use a horizontal signal proportional to time, we will see our first terminal. Here, my signal as a time function using internal sawtooth generator. What's the name? Device? Oscilloscope. Oscillations. Googling. scope viewer. Oscilloscope use, classic oscilloscope use visualization in the space of time proportional signal to make it visible as a time function. Changing this constant, so rising constant, I can have different man така, notar bija beigušies. Nāciet nākamreiz.
Jā, labi. Tas vienkārši nevar nākt tagad, ja?
Notar bija beidzas.
Jā, labi, labi.
Man te bardaka nebūs.
Labi,
So, changing the rate, I can have any time scope. Okay, actual internal capacitance limits me. But everything possible in some, let's say, within some limitations. Okay. Change frequency, see difference. I can switch back to come back, please. There is a small difference in frequencies, and we see figure rotates. Actually, depending from the view angle, it's rotates left or right. For me now, it's rotates right. Research figure. Image of one thing be image in space of another signal. Here both are sine, both are ideal harmonic signals. Now it turns left. Okay, so basic of oscilloscopy, the signal visualization is representation of the one signal in a crafted space of another signal. We will use this functional representation or functional imaging as a very capable tool of signal analysis. Okay, should I? Yeah, I need another idea about signals. This one is clear? Maybe some questions? Okay, I will switch the scope off, and I would like to speak on one characteristic of signals. There is one idea with periodic signals called effective value. What's the idea? I can have, let's say, this one signal like this. Or another like this. This one is taller. This one is wider. How to compare them? One idea was introduced. Let's say we have an active resistance powered from DC source. It will heat, producing, let's say, P1 watts of heat. We can load our signal with the same resistance and it will produce some thermal power. Second, I will switch screens. Comparison idea is like this. In terms of energy, this DC source will be equivalent to my signal if produced powers are equal. Anyway, we pay for energy. Matter shows energy. So in terms of energy, they will be equivalent. For DC power, everything is simple. It will be multiplied by current or divided by R. So it will be E squared divided by resistance. It's very simple. For signal, little bit complicated. Let's assume that our signal is periodic. For each time, each moment, we will have instant power as our signal squared divided by resistance. It's an instant power. Total energy within one period will be what I'm doing, sum of all instant powers. It's an energy within one period. Average power, let's say power on the meter, what is watt? 1 watt. 1 joule in 1 second. So, it will be 1 against average. Yeah. Is it clear how I got this? Why I need an average? I got V capital joules of energy within T capital seconds, within one period. So watts, what will show? Case wattmeter. What will wattmeter show me? Energy within one period divided by period time, average. Now, E squared divided by resistance equals 1 half squared. This one goes, so equivalent EMF will be square root 1 against period divided by sum of signal square from time. This value of equivalent DC source called often called RMS value, root mean square. It's an energy equivalent of the signal or effective value. When someone tells you that there is 230 volts in the outlet, 230 is effective value. So for it's defined strictly only for periodic signals. For periodic signals, I'm going to use S effective or RMS root mean square of my signal, and it will be square root 1 against time. For harmonic signal, this one, this formula produces square root from 2. Or cosine. This formula yields coefficient square root from 2. It's a classics of electrotechnics. The reality effective value is defined for any periodic signal. And effective value is what we will pay for. One day I will put this thing in service. Ever saw something like this? Prepay method. Want to watch TV? Put a coin here. Prepayment. Not a, now models with a card are popular, and this one was coin operator. This older model, Britain's one, in new converted to new pennies, but it works. Someone took the coin. So method counts energy to effective value. This is how we pay. Yeah, we in future we will convert it to discrete form. For how there are two ways. One, perform Fourier decomposition and calculate each harmonic, or like methods do, they often simple integrate. Like RMS meters. Okay, where we are. I took 10 minutes. Maybe some questions? I don't want to start Fourier decomposition. I think it will be good for next time. Okay, I think it's enough for today. Yeah. Yeah. I hope sound recorded.